So now we are going to discuss the very basic things, that is your like the operating charts. So here in today's video I am going to discuss operating charts of a large turbo generator. So before I start, I just want to let you know that what is operating chart of a generator. Like once you are considering, first try to understand one thing, that if you connect one generator with an infinite bus bar, the generator is supposed to share a percentage of your existing load connected across that infinite bus bar. However, the generator itself will operate with some power factor. Try to understand that if it is an underexcited generator, then it will act with leading power factor. If it is an overexcited generator, it will act with a lagging power factor. Now, here, how can we determine that for means how the generator will behave once we connect the generator with the infinite bus bar? And means what about the generator? Its operating charts, you can consider it's like your performance card, means your grade card. From looking at a grade card, not only your CGPA, we can figure out your CGPA, or how good or means on an average how good or bad student you are, means bad in terms of performance wise, academic performance wise, but also it gives a clear indication that what was your performance in different subjects, like how well or poor you performed in say engineering mathematics or engineering mechanics or in physics. What was your this once I get your grade card, I can see, okay, he or she was good at physics but not so good at say in chemistry. So we all means we could figure out that. So similarly, this operating chart gives us a complete characteristics information about our generator. So before we proceed, let us understand that how things work. Like what is the need? Need is that when we are looking for selection of a large generator, the main factors while we try to select a generator, what are the main factors? One is your uh, rated MVA, and I can say its nominal power factor, right? These two will also, like how these two are important and why these two are very important, that we are going to discuss, and how power factor can alter the field winding, heating and cooling. All these things we will discuss. But what is here, that suppose you know that your uh, like your infinite bus bar is going to supply a particular or cater the demand of a particular load line, then based on this two factors, you can determine that what would be the load shared by this particular generator. Suppose you are having a generator X with you that is not yet connected with your infinite bus bar, and its operating chart is known to you. Then you can understand that how the system will perform once you connect it with the system, means infinite bus bar. Like in terms of say, it is like you are thinking about student performance or would be performance in a project, like how a student would perform if you induct him or her in a project. So depending on your project topic, you may understand that this is the means level of mathematical skills or analytical skills required. This is the amount of hardware, means and passion for doing something in hardware is required. So all these you can figure out from his or her career, means how good he or she was in laboratory. From that you can draw some inference that how good or bad she will perform if you induct him or her in your project and give him or her a chance to work on your field. So the same thing we can figure out from these operating characteristics. Now, to avoid unnecessary complexity, what we will do here, we will disregard two things. We will disregard armature circuit resistance and saturation. So if we disregard these two, then let me just very simple manner try to means discuss what is here, that if you are connecting or going to connect a machine with an alternating bus bar, then the terminal voltage of the machine will remain constant, that is V. Now, after connecting, if the machine is going to deliver a current I at a lagging power factor angle theta, then what you will have? You will have here, sorry, here you will have yes. This is our, if this is I, this is our JIXS, and then you will get your E. So Vt or V, this is constant. You can't vary. Now what you can vary? You can vary this angle delta, right? And one thing that is very interesting to note here is that if we think about this, then what is our power? Power is P is equal to EV by XS sine delta, right? Now let us consider these V and Xs are constant for a given machine and operating with infinite bus bar. V and Xs is constant. So basically, isn't it that we are dealing with something that is proportional to E sine delta? Now, what is E sine delta? E sine delta is something that is means if you extend this line of Vt, then whatever projection will be drawn, this is your E sine delta, correct? Now this gives us the power. So we can draw two line. One is by keeping our Ex's like keeping E constant, and if we keep on increasing our input, then what would happen? Prime mover input, we will have a different value, means different E here with a value of delta dash, where delta dash is greater than delta. And clearly from this diagram you can see that if you draw similarly, you are having a value of E sine delta is less than sine delta dash. Another circle what you can have is that if you do not alter delta, like if you keep delta constant, but if you start or we start varying this E, so by varying E, what you will have, now obviously if you vary E, what would happen? It is like you are applying means you are changing voltage difference across a fixed reactance, that is XS, and therefore the current will change. However, if we are keeping delta constant, then this will remain constant, but and also V is remaining constant. But if you increase this E like this, then what would happen? This will become, so clearly you are getting that if we increase E, now this saffron color dashed line, that is indicating I dash XS, clearly that I dash XS, this I dash magnitude wise, this I dash is greater than I, and needless to say that I dash is actually indicating a more lagging current, because otherwise since you are keeping this E sine delta constant, so your active power will remain constant. And if you change this theta, like if you consider I dash, now I dash is having a different angle, but what is required, that the projection on your Vt must remain same, otherwise the power, if you disregard armature reaction, then you are obliged to make these two same, they must be equal to this one. Now if you are not changing the sine delta, this P will become constant, so this Vi sine theta and Vi dash cos theta dash must be equal. Therefore this I dash, you can see that if we change E, so what we can consider, it is like this point, this operating point, how we can determine, this is actually intersection of two different arc. One is your the arc of constant E, centered here, and it is, say it is O, this is E. Okay, let me use a different color to give you the feeling. So again, let me consider that what about this one? It is like, if we consider this operating condition, it is one is for constant E, another arc will be there depending on our, from this point, because this point is also constant with respect to O, because V's magnitude is constant, you are having another curve. This is due to their intersection gives me the operating condition. So once we are considering like adding a load with our generator, means an infinite bus bar, we can figure it out. Now let me show you the exact diagram that is drawn in scale and more accurate. I am delivering this lecture based on this diagram. I have taken it from the book of M.G. Say. It's also a celebrated book. Well, means referred and means very good reference book. Anyway, so this is a chart for turbo generator. Now we know turbo generator are high speed generator, and therefore they are of cylindrical rotor type generator. Now if we consider the turbo generator, for this is the diagram that I was trying to explain you, right? Now see this turbo generator. Here what is happening, that uh, now, like I have already explained it to you, the side diagram. Now come to this large chart. First let me take a different color here. So how this chart was constructed? First of all, for this chart, let us consider a synchronous reactance that is 167%. For zero excitation, means if you keep the excitation 0, then what would happen? Your E will become 0, and for that value of E, what would be the value of your V? Means V remains constant. What would be the I? I will be 100 by 167, that will be 60% of your, roughly 60% of your full load value. So this represents 60% of your full load MVA, means this we are getting from our short circuit one. So like this point, you can see here that this gives us, this is 0. Now here this gives us the point where for this side is active power and this side is for our MVAR. now this here when you do not excite, then what would happen? The machine will absorb leading means see again from the infinite bus bar, a machine that is totally unexcited, the infinite bus bar will observe means will realize that as if it is feeding a purely reactive load. But how your generator will see? Generator will see infinite bus bar as a source of pure means that infinite bus bar will sense a pure lagging load connected to its terminal or connected across it, and the generator, if you sit at the rotor or you are sitting at the place of induced EMF, you will see a perfect leading current is flowing towards you. So here you can see that this 60 is gives us this 0 to 60, it gives us the value of our means the value of current that we are getting. Now this like for this 60, what we can do is that now what we can do is that from this line the this gives us the like now this MVA is in full form of MVAR, and this fixes like whatever will be the scale for MVAR, the same scale we need to apply for MVA also. Now a vertical line, that is OV, we have drawn and scaled 60% to our full load MVAR, right? Now similarly this side is leading, like generator is absorbing leading current, and that side is lagging current. This is when your voltage, like today Ayushman asked that what about condition when it will be floating. So this is a condition when your generator voltage and terminal voltage are matched. Now if you come here in this direction, then your generator voltage is so small, you are actually absorbing leading power from the infinite bus bar. Generator is drawing leading current, and here it is drawing the lagging current. Now see here what we are having that, but try to understand that uh, here means still when you are not providing any excitation. Today I mentioned one point that if we disregard resistance value, then all this is happening. So once you disregard, then only you are getting your underexcited V, means that when like you are not giving any excitation, this point is here at 60. Otherwise you could have it, it would give you some value in here in negative direction. This positive active power megawatt, it gives the generator output, but in case of real generator, if you consider the resistance and do these things in a very serious manner, you would get your point somewhere here. Anyway, now uh, back to there this diagram with our assumptions. So these are like now from V we can draw a horizontal line. This gives us active power. You can consider this the circle that we drawn for V by 2RA, that type of circle we are 2R circle we are drawing here. So these are all our active power in megawatt, right? So now this active power in megawatt, here it gives us 0 to and circle of percentage excitation. Here you can see that we are having circles of different excitation. This one is this side. Let me shade. This is our under excited region, right? This side is under excited region, and what about the other side? This side is overexcited region. Then obvious question that comes in your mind, that means there is no bound, like we can keep on means increasing the field current to any value, like here we can see 250 degree, 260 degree, sorry, 250 percentage, 260 percentage. uh, can't we make it 300 percentage or something? Or if it is only 260%, then what was the factor that limited to that only 260%, not beyond that? So basically, you instead of using the whole region, you are able to use this part, and only this part, that is under the this shaded or uh, dashed black card. Why so? Here lies the means question, and we'll try to figure out the answer. Well, so this side is underexcited and this cyan colored side is overexcited. Now try to understand that how we are getting this. Taking 100% of your megawatt as the maximum allowable power, like this power, you can draw a vertical line like this line is given by your prime mover. Now, if we assume that the machine is like rated to give 100% of megawatt power at power factor point 9 lagging. Now, this point 9 lagging, this determines this point Q. After that, what will happen? This like now see that in can't like we can't have a card like this. After Q, we were obliged to make it bent. Now, can you think about anything that this arc or this arc between Q and indicates? We can have a card like this, like we could means draw it a straight curve. First of all, this radial distance at any point, if you see this side means like a layman, if we try to analyze, this side is your this vertical side is for your MVAR and this horizontal side is for megawatt. Now if you keep this megawatt side constant and keep on increasing this MVAR side, so what is going to increase? Obviously, in addition to your MVAR, it is going to change your MVA. But that MVA, obviously, when you are discussing or taking a particular machine, then the machine stator current. So this part is due to stator current. This side is due to prime mover. Like if you want more power, prime mover will say, boss, find a new one. I won't be able to give you more power. So this vertical line that prime mover will give. Now this one, like here, if you consider, then from N, who governs this arc? Like even if we consider, if we, why can't we maintain a constant MVA arc like this? Who stops us? Why it is from N instead of having this, like whatever drop, if we follow this circular arc, the dashed one that I just drawn, then it would imply a constant MVA. That means you are reducing the megawatt, but you are increasing MVAR. So this is limited by your field current, because if you want more MVAR, then you need to increase the amount of your field current, and that field current will cause definitely a heating in your field winding. So that is not possible. Therefore, this side is bound by your field current. Now, this okay. Now this all these are drawn. Then why this side? This side there was no such bar like we can have it. But why it is between SUT? Think about it. Like what would happen if we consider this means we can why can't we have a straight line like this? Who stops us? Or like this is this side from n to this side, this is due to field current limitation. Q to n, this is due to stator current limitation. This uh, q to s, this is due to prime mover limitation. Then what is something, or what is the factor that limits SUT? Why can't we have this is like this? Because our theoretical stator limit is that it is like we can have our theoretical stability limit is equal to 100, no, sorry, 90 degree. So what stops us from realizing that angle? Take a moment and just think about it, that what stops us from. Even you must be surprised that what means, I think I have already given the answer, because I said that beyond this some stability, I uttered the word stability. However, how this operating chart stability is determined, like theoretical stability limit, that is the maximum value, we can't have it. Then how we do it in practical case? In practical case, we just do that whatever be the value of MVAR, then that, like suppose what is your 10% of your, like 10% of these will be deducted. Like at first it is, instead of 60 we consider it 50. Then what we did, 50 means when we come here at this point, here not only that 10% means from 50 we deduct this much amount. This amount is proportional to the value of this megawatt. So as we go on increasing in this megawatt range, you can see it is almost like a triangle, means notes, like triangles whose these sides are like, what was that triangle? I just forgot the name. Like in geometry, we used to do it this kind of triangle. So here you can get it, that how who limit you from extending it to totally downward, rather you stopped at S. This side is due to your stability limit. So once again, how we started means you can start in a reverse way. First, you consider machine is not delivering any active power, and you got only connected that generator with the infinite bus to supply it reactive power. So obviously your delta is 0, but you are increasing this E to any extent, but then you realize that it is somewhat to 60% or something below that, you can't extend. Well, with that excitation, you now keep on increasing your Means if you follow this arc is of along this arc your reactive power constant. So then once you reach this point N, however what is changing along this curve, your active power is changing. Once you reach this point, then here your MVA is constant. Thereby your reactive power is not same, rather it is reducing in proportion to your this kilowatt power. Now once you reach here, your active power is constant. And then this fourth side, that is governed by the stability limit of your machine. So I hope this is you understand this construction of this operating chart for a turbo alternator. Similarly, we can construct the chart for like Salient pole machine. Problem is that when the quarter in which you live, it is selected for quarantine purpose. There are people, means the students, now they are playing different musics based on their tastes. What they are trying to do, it's a very simple thing. Just a minute. Now here this is for Salient pole synchronous machine. Now I have taken again these cards from the book of MG Say. Now here one thing that is clear, that this part you can see that what is the difference is shown in this first two curve, that is due to this one, like the saliency, that is xsd minus xsq. Like if you disregard this saliency, then clearly you will get means you can draw this diagram from this point Q as like a cylindrical formation. But once you consider xsd is not is equal to xsq, you won't be able to draw it. And this is the amount, that is the minimum, like this one is due to the second part of our equation, that comes due to the reluctance term, like these two different reactants xd and xq, and as long as we cannot have them equal, we can't have this equation. Like this equation, these two equations are actually identical, just here all the sides of this phasor is divided by x is d, this one. What is your xsd? What xsd is direct axis synchronous armature reactance. Direct axis armature reactance, xsd. Sometimes we might have referred it like xad also. It's not a big deal. What we have done is that we divided everything by xsd. So once we divide everything by xsd, it is giving us these values, like what we are getting. Now see that this is the difference between these two we are getting here, and this one, like this is ET is also proportional to IF, so it is IF by XST. Now let us start our discussion from figure C. Figure C is that the excitation corresponding to full load at leading, means for a constant current for leading load and at a lagging power factor. These are shown in your figure C. Now it may be observed that at low leading power factor the excitation will have to be reversed on account to that effect of direct magnetizing armature reaction. This is very important observation, that for only we are considering the generator case, not the motor part. But what it tries to point out is that if we consider the excitation that is corresponding to full load current at a leading power factor, then we will see that at low leading power factor the excitation will have to be reversed. Why it must be reversed? Because until unless you reverse it, you cannot take care of direct armature reaction, direct axis armature reaction, that is magnetizing in case of your armature current. So that is what is required. Now with this, and we have already shown that we discussed it, so we will see its reflection in our figure D, where we can see that for constant excitation we can find out an appropriate locus by drawing that rays from Q. However, for low voltage, like when I discussed it for Salient pole machine V card, we had a reentrant loop for our Salient pole synchronous machine. So that was the case when it was evident that this part I'm talking about, this was that formation of reentrant loop what we were discussing. Here in the word of MG say what he said, for it is also a good technical term, that we are having lima core here, means instead of having circles of concentric circles, we are having lima core here at this point, and the shape it becoming more evident with small excitation, and that gives the birth of this reentrant loop. Now here with this I'm not means just we can do the load rate, like governor rate chart. Here in this diagram you can see that all these remain same, that how these points are coming. However, there is slight difference you can observe, like in case of your for your reference I would like to go to back to that. Yeah, here you can see that this is constant power limited, or the constant is imposed by prime mover. Then constant MVA limit is imposed by your stator current thermal limit. Then it is that reactive power constant constraint imposed by your field current and field cooling aspect, and this side of the curve is your stability limit. And how we got this? For each value we just need to subtract from it was 60 gram from that this short circuit impedance term, and then we consider the stability, that working stability is at least 10% less than that what is the theoretical stability limit, and we keep on subtracting and got this value. Now what happened in case of our this one here, it is somewhat not clearly, this is not identical with what we studied for our cylindrical rotor machine. Here you can see that like you can construct rate chart, and this it is like low excitation. What you are having here, you are having these points. Now see what we are getting. The machine is presumed to have a full load rating at power factor of 0.9. Then this Mn, this Mn represent the excitation limit. This side is for rotor heating. Then here we are having what we are having, prime mover mechanical limit. So obvious question will arise that what happened to our in this side, what happened to our, like, why we are not considering that MVA limit, or it is like if you consider or compare side by side, then it was an MVA limit, but here it is so high MVA limit is not considered here. But where we are getting this MVA limit? This MVA limit we are getting between this point S and Q, that is near the leading region. So what is that difference? Like in case of turbo alternator we got it in lagging power side, but here we are getting it in leading power side, right? Why so? Think about this. And then when we get this SQ, this portion is our MVA limit, and then this QU, it is the practical stability limit. We found it using same same type of analogy. So this is stability limit. Now, and this region is typical region. It's due to the saliency of the rotor and what we discuss for that C, figure number C. You can explain it, but first you think that why in case of turbo alternator it was first rotor then MVA, and now here it is means MVA's maximum MVA limit case is occurring in the leading side. Why so? That we must understand. Okay, now we will discuss only one small thing and then we will conclude. The topic is load sharing between governors. What does it mean? Every governor is like means is does exhibit this kind of characteristics. While if you increase the megawatt power output of the governor, this is the frequency or speed of the governor that will fall. So if you have one alternator or means one class of alternator that is at when it is no load it is running at 52 hertz, and when you extract 5 milliwatt the frequency falls down to 50 hertz. And say you are having another class of alternator that is having means start at 53 hertz. So what is the slope of this one? This is having a slope of, in terms of load, if you try to find out, the slope is 3 hertz by 5, and for this white one it is 2 hertz by 5. Right? I am talking about frequency by watt. Now what would happen? Suppose you have a 8 megawatt load. Now if you consider the two identical alternators are acting together, so 8 megawatt load, as they are totally identical alternator, so they will share equal amount of load. That means this is 4 megawatt, this is 4 megawatt, and in that case if your load drop to 6 megawatt, this is 52 hertz, this is some hertz, you can find out the frequency hertz from that slope of that curve. Like this point will be 52 minus this will be the frequency of this point. Probably will get it is equal to 50.4 hertz. So anyway, at this point, then if you further drop the load, means load drop means somebody who was absorbing electrical output from the generator's output terminal just reduce its demand. Suppose it was evening time, it was 8 megawatt, and in night time around 11 pm it drops to 6 megawatt. In that case, as they are identical, there will be 3 megawatt power sharing. And what would be the frequency? Frequency will become something like so. This will become 2 by 5 means correct. Now see that this is what is happening here, that when you reduce the load, the change is taking place in identical manner. However, what would happen if we do it for generators that are not identical? Suppose the generators are totally identical in nature. So once they are in synchronization, they will share equal load. Right. Although due to my bad drawing, it seems that they are not sharing equal load. But you can see that both of them are sharing 4 megawatt when they are at synchronization. However, if there is a sudden jump, then what would happen? That same kind of things you will be able to observe, but this shift like 4 megawatt and 4 megawatt now means if this is your 8, then in proportion with that you will get a 6 megawatt line. You will be able to draw a 6 megawatt line in scale with that. But here one strange thing you will observe, that the load shared by the generator having a small slope is less than the one that is having a steep curve for, or means a high rate of change for your governor speed torque characteristics. Again, I am telling you, all these are with respect to governor speed torque characteristics. If we introduce a sudden change, then how the two generators are going to behave. That is what we are trying to figure out from this discussion. Once I upload all the theoretical videos, then I'll solve a few numerical problems, or else you will find the numerical problems, plenty of numerical problems available in many places, so you can also find out, and solving one or two numerical problems on this particular topic will clear your viewpoint. So in my next lecture I will discuss induction machine.